So yeah, this presentation is primarily about why you would want to consider using top-down design enabled by Wave. Brief introduction of myself. I've had a lot of experience with respect to this. At GE Aircraft Engines, I developed their Wave-enabled top-down design structure, which takes the output of preliminary design you see here on the left and creates an initial 3D design infrastructure of parts in which detailed design can then begin. They still use this design process today. I came to Siemens. I basically consulted with clients around the world on using Wave-enabled top-down design, some of those clients being down here. And then I went to Aerospace for a stint, which is a startup designing an all-electric plane. And I use these methods to connect the detailed designed plane to the aerodynamic shape using top-down design techniques. And now I'm back here at Siemens PLM in the Industries Group. I'm the A&D Solution Director, Aerospace and Defense. So just kind of a reminder or an explanation to people who might not understand what top-down design is. Top-down design is a system that defines the components. So in this example, we start off with a aerodynamic shape of a plane. We break that up into its fundamental building blocks: a fuselage, a wing, a horizontal tail, further down into an upper wing, a lower wing, a wing spar, until we get down to the bottom and we have the individual components. And these are all connected using Wave, which is shown here in red using NX Wave. So it's an associative copy going from one part file to another part file. And the flow of information is top down. The information starts at the top and it goes to the bottom. Does that all make sense so far?
Yep, and on something like that, you'd be starting with the outer surfaces generally then, and then using that to drive everything downstream from there. Okay.
Yes, and that's for a plane. For another product, it might be something else.
Right.
What is the primary geometry that is kind of finds its flesh in conceptual or preliminary design and then drives all the detailed stuff? What is that? And it's going to be different for different things. And this is just an example for a plane. It's the aerodynamic shape. It's everything.
And will you show an example of how you structure that in an X assembly also during this presentation?
Not in this one. This is again about a why. The how-tos are in another presentation, which I'll go over.
Okay.
So that's what top-down design is: a system that defines components. And the benefits of top-down design is it enables a structured and accurate distribution of the primary geometry down to the design team and the components below. The design is driven by design intent, not manufacturing intent. The changes in the primary geometry or interfaces can be driven down to the whole team in a very robust way. The primary components are designed in what's called product space, in their place in the product, and it's a design it's a design engineering productivity and risk reduction tool. So bottoms up design. So bottoms up design is traditional CAD design, where I have a bunch of components down at the bottom and I want to assemble them into a product. So in this case, the information flow is from the bottom to the top. And the components are driving the system with manufacturing intent. This is how the things are going to be made, and they're in their detailed form, and it drives up to a whole system at the very top. Excuse me. So the benefits of bottom-up design: it collects all the design components, whether you design them, suppliers design them, their end item LRUs. their detailed landing gear, whatever it is. It collects all of the components. It positions them in product space. It provides the ability to add in non-geometric products like grease or cleaning fluid or whatever that might be. And again, this is a design tool, design bottoms up. So you can also have stay out space claims, kinematic space claims, people. You could add in the adhesive so that you can do weight and CG of that. And it provides kind of a design sandbox for the entire team to see what the entire product is going to look like, and provides the design hierarchical view of the product, typically functionally based. Okay. And then if you combine these two things, the entire design can be rapidly and robustly driven by primary system geometry. In other words, I take the output of the top-down design system and I put it into the bottom-up system. And this is a fraction of the actual components. I add in everything else we're going to buy, which is typically 90% of what's actually in the BOM, and then that builds up to the actual product. So these things, and working in concert together, you're able to rapidly make design changes. Also, in the long term, you can use this. So within a program, you can manage your primary geometry to the components below, but you can also use this. You can create a template out of this, and then be able to derive a new product that's similar in nature, and start with a new aerodynamic shape in this case, and then the underlying things, because they're driven by design intent, should robustly morph. So you're not starting from scratch, but you're using an intelligent kind of rescale, if that makes sense. Okay. Some customer proof points. Again, this was done at GE. And so from conceptual design to initial 3D CAD, this is able to be done in 1 week by one person. So they go from this to this in 1 week. And before this process was enabled, it would be hundreds of people over months. And it's very robust. Similarly, this was done at Biospace for a 2C plane. I managed that. And they underwent two major aerodynamic shape changes, which affected essentially every single component in the plane, which is over 3,000 parts. And they did each of those in less than 1 week. And here's a video that kind of shows this in action. So I have the equivalent. This is an example of a rocket an intern did for me here in the summer of 2022. He has a very simple rocket in a single part file with space claims for fuel tanks and a payload and stuff. He then feeds that into a top-down structure where all the components are derived in more detail, in this case, almost full detail. And then he has a bottoms-up version over here that has all the components, and you can see they're in more detailed shape. They've added in things they're buying, and so on and so forth. So I'll play this, and he has configured this with only two major parameters, which is the mass of the satellite and the diameter of the satellite. He can reconfigure the whole thing. So that happened very quickly, but it's going on in this conceptual model here. So he makes those two changes, and you can see right there that the shape changed, and now he's going to update through that top-down structure in a very robust way the top-down structure to detailed components, but you're actually going to see it being mirrored in the bottom-up structure over here. So he's again making that change. I went back a little bit. He says, okay, that happens incredibly fast. This is all physics-based. And then he's going through major section by section and updating that. You can see the fins just changed, the fuel tanks just morphed. Now the main body of the rocket is changing shape to accommodate that. And that's happening here. This whole update took about 5 minutes. He squished it down into 2. Now he's working on the upper stages here. So similarly, the fuel tanks are morphing. They're finding their new spot. The engine got a little bigger. The payload got a little bigger. The outer structure is changing to accommodate. And finally, a similar thing's going on with the nose cone. And that was basically the design intent that he followed. He was working from the bottom up.
That's very cool.
You saw how that all worked.
Yeah.
It didn't have anything to do with how the rocket's put together. So this is a design hierarchical bomb. What is the functional design intent breakdown going through this top-down design structure? And he went basically from this area here to this next area here, here to here. So the influence was following that path. So
that demonstrates it very well.
An intern did that, who had basic NX skills.
With some coaching, or
with some coaching, but
yeah, it's the modeling skills you're saying is like all it was there, and with the coaching and the behind the scenes like theory of how you're doing it, then that's what takes the years of experience to get.
Yeah, but he got it. I mean, once in the how-to document that I'm going to present next, I just went through that with him, and he basically just followed that. And then he would have questions. I'd answer them. It's, you let wave go, and it's the Wild West. It can actually become a challenge.
Yeah, we've got
wave relationships that you don't understand what they're doing, and so you have to have your hand on the pulse of what's going on. It's good for 2 reasons. In the short term, you're keeping your design team all synced up with the primary geometry and the components. So any changes that need to take place, you want to avoid them, but if you need to do them, you can do it. In the long term, you can use this to, now I've got this working rocket. I want to change payloads and make a bigger rocket now, a different class. I'm going to use this template to morph it into a much bigger rocket. And then just going to, again, summarizing here, you can have direct and robust connection of the primary geometry to the components below. In the short term, changes to that geometry can be conveyed in an associative way robustly down and rapidly down to those components. In the long term, that primary geometry can be morphed into something much bigger that might be a different class of plane or whatever. And then you can convey those changes down to a new set of components below. You would most probably clone off this whole thing to a new product with new part numbers and all of that stuff. But then you would make those changes. And again, it's a design engineering productivity and risk reduction tool. Okay, so that's kind of the why. Why would you want to do this? Okay, so this is a best practices presentation that I've honed over the years about wave-enabled top-down design. It's a very powerful tool, and it can yield fantastic results if you follow robust best practices and understand them and convey that to your design team so that they follow them as well. So this is how to do this. In the previous PowerPoint, I talked about why. So I've broken this up into kind of 4 major groupings, with one of them being kind of a 2-part. Level setting what we're talking about, what are the primary goals, and then the best practices themselves, primarily methods, and then some technology as well, and a summary. Okay, so the first part, we're going to do some level setting. Again, who am I? I did this I led a team of about 50 people at GE Aircraft Engines in the 2000s time frame. And we developed a top-down design system, a wave-enabled top-down design system that they still use today, taking the output from conceptual design and creating the initial design infrastructure of 3D parts for the turbofan. When we got this refined and released, this process would take one person about 1 week to do, versus possibly hundreds of people months to do. I then came to Siemens, essentially consulting on wave-enabled top-down design with clients around the world, some of them being here. I then led the engineering team at Aerospace here in Denver, who are designing and certifying a all-electric plane. And we were able to associate the primary geometry to the detailed geometry. And within this process arrow here, we did 2 major redefinitions. I shouldn't see, we've modified the primary geometry twice. And that took, with all the detailed components, and it took a team of 8 people working from their homes over Wi-Fi during COVID, 1 week to do that each time. So it was pretty amazing. And now I'm back at Siemens, and I work in the industries group, and I'm the Aerospace and Defense Solution Director. So again, this is a how best practice. We're going to talk about the tip of the iceberg here. I'm not going to talk so much about the whys. This is something that I've gained in experience over a career of doing this. But it yields up into, these are the rules of the road. If you follow these rules of the road, things will work out well for you. It's generalized, and again, they are the tip of the iceberg. And this is key. If how they apply depends on the specific design processes and the use case that's being worked on. For example, how you would use this in a airplane might be different than how you would use it in a replacement knee. But if the best practices are still the same, and how you would choose to apply them once you understand them, it would be up to the client to figure out best. Kind of Wave 101, what is Wave? It's an out-of-the-box capability to distribute geometry from one file to another and convey change of that geometry. Only use wavelengths if both conditions apply. This is very important. Do not use wave as a cheap and easy means to copy static geometry from one place to another. The geometry should be assumed to be dynamic and change, and so wave gives you the ability to convey that change. Only use a wavelength then. If you're using wavelengths to copy geometry and that's all you're doing, you're burdening yourself with a lot of overhead. So just copy paste. If that's what you're doing, just copy paste. But if you want to associate and convey change of that geometry, then you use Wave. Okay, what is top-down design? Top-down design is a system that defines components. And so I start off with the primary geometry of an airplane, and that geometry going through this top-down structure defines the detail structural components below. And the flow of information is from the top down to the bottom. Conversely, bottom-up design is components that define a system. So it'd be like if Ford drove up to my driveway, dumped all the parts for a Ford Explorer on my driveway. Here, you put it together. That's what the bottoms-up assembly does. The flow is from the bottom to the top. So you have all these components below, and you have to organize them in a way that they make a product at the top. It's important to note that in top-down design, you're talking about some fraction of the BOM as far as number of components, usually small fraction. With bottoms-up design, you're talking about all of them.
Okay.
All right. Goals. The highest level wavelength goals. All the best practices are related to trying to achieve these goals. And they are configuration control of the dynamic geometry, only intended wavelength updates, robust interpart relationships, rapid geometry updates from source to destination, avoidance of circular loops, and compartmentalizing of degrees of the product's degrees of freedom. So an airplane, for example, probably has millions of degrees of freedom when they start off designing, but you can compartmentalize those degrees of freedom in different nodes of that structure so that it's a more manageable problem to solve. How are these accomplished? Through overtly clear one-way flow of all interpart relationships, not just wave, interpart expressions, promotions. There are a number of interpart relationships. Wave is kind of the king among them, but this applies to any interpart relationship. And traditionally, the means to accomplish this is through a top-down design structure. The assembly component hierarchy represents the breakdown of design intent, driver-driven relationships. So that's the white lines, that's the hierarchy of the structure. Wave is how the geometry is dynamically shared throughout the assembly. Those are the red lines. All right, so I use the assembly component structure to kind of lay out the hierarchy, but then I use wave to transfer the geometry in an associative way, right? So some things to consider. If it's appropriate to use wave top-down design on your product. So here's some things to think about. The primary product input should be clear. The primary product geometry is anticipated to change during the program. Again, going back, if it's not anticipated to change, it's static. There's no reason to use wave. So don't use wave. Use wave if you anticipate it's going to change. And in my experience in 38 years of aerospace design, it always changes. So just assume, and you'll be happy that you did. You hope you don't have to use it, but you've planned for it. The primary geometry topology is reasonably stable. In other words, going from a small coupe to a medium coupe, that's the topology of that is the same. Going from a small coupe to a medium pickup, that topology is completely different. So it's very difficult to do that. The product is functionally driven. The design breakdown into more fundamental subsystems and components is well understood. The subsystem component design rules of thumb are known relative to how the primary geometry is anticipated to change. For example, scaling up or down of a payload or range requirement. The components are uniquely positioned and can be designed in product space. So you wouldn't do this with a bolt. There are bolts used all over the place, but you would do this with a wing spar. You would do this with an upper right skin and so on and so forth. They're unique. They're unique to that product. They're uniquely positioned. A working coordinate system can be used in components to provide a local 0-0 coordinate system relative to the component geometry. Sometimes this is a desire for people who are used to SolidWorks, and they like to see their component at 0-0-0 or their subsystem at 0-0-0. So do that with a local working coordinate system. So I have kind of down here a spectrum, good candidates. Here's a replacement knee, 100% function driven. The geometry is known, and so on and so forth. So this is a very good candidate here. An airplane, very much function driven, some styling. A car, function driven, but a lot of styling. Styling is less of something that can be have a design rule established around it. It's more of an aesthetic. So again, what's the driver driven and what's the relationship between the driver and the driven? With aesthetics, it's more like maybe this, maybe that. So as aesthetics come more and more into play, those driver-driven relationships are a little more difficult. And here's an example of something that's poor. This phone looks completely different than that phone. But phones now are starting to look pretty stable. So as phones kind of firm up from an architecture and a topology and a function point of view, they're going to start sliding down to the left. And you might be able to use Wave to design some of that phone.
Jim, on your last point there, the components are uniquely positioned. Are you saying that the product can be designed in its own part space, but then it's going to reflect a different space in the assembly?
No, the opposite. The part is designed in product space.
Okay.
So if you go into this winglet here, it is, if you open that part file, it is actually out there in that part file in that space.
Okay. Makes sense.
A bolt,
right,
you wouldn't do that with. A bolt, you would do it in component space or at 0-0-0, and then you would position it wherever you want in the product. So they're not uniquely positioned. And so that's different.
Okay. Thanks.
Makes sense.
Yeah.
So again, bound the scope of the top-down design structure, determine its output. What is it going to be used for? Detailed features, defeatured components, design space claims, interfaces alone. These are all valid uses of a top-down design structure. Bound the design change expectations. Again, going back to the example of, yeah, I can have this top-down design structure and make it, and I can morph from a small coupe to a medium-sized coupe. But if I want to change to a pickup truck, it's going to break. The topology is fundamentally different. So bound the expectations of change. And bound to components internally designed is, in my experience. Also, when assembled by themselves, would be recognizable to a layman as representing the product. Can be designed in product space, form the foundation of the product, and around which all other bottom-up components can be oriented, and for which the design rules of thumb are known. So kind of from a percentage BOM point of view, this replacement knee, 100% of the components can be designed in that top-down structure. It's every single part is going to be designed here. But as we work our way to the right, most probably only the structure of the airplane would be designed using a top-down design structure system. Everything else, they're probably buying the engines, the avionics, the radar systems, and you're going to use bottoms-up design techniques to position them in the bottoms-up structure around these components. Similarly with a car, you're probably using even less of it. More parts are being bought. And then with a phone, again, this example, you probably wouldn't use it at all. All right? That's kind of from a percentage BOM point of view. So for the Eclipse 500, this example here, you probably only use it for the structure. You know the design rules of thumb. You know where these things go. You know how they're going to change with primary structure. And this is probably what you're spending all of your time and money on. The rest of the stuff you're buying and are going to orient it around this. All right, so focus on the things you and your team are designing. Best practices with respect to all of the stuff I just talked about. We're talking about methods here. Design the upper levels of the top-down design structure with the intended user's skill set in mind. So think about what you're doing here in this structure. Think about what your resources, what their skill level is, what the bottom of the structure, who are the component owners, what their skill level is, and design it considering all of those things. Don't make it so powerful but complex that they can't use it. You want something that does what you want it to do, but is usable by the users who are intended to use it. Proactively coach, mentor those users on top-down design best practices. I find it's best to limit access to the upper levels of the top-down design structure to a few of your most skilled SME users. The rest of the users should be bounded to being component owners below. Enterprise consumers, supply chain, whatever they are, they should have no access to the top-down design structure. In fact, they shouldn't even know about it. They're only going to see stuff through the engineering structure, bottoms-up structure. The top-down design structure is purely a design tool and is a means of producing components. So it's overwhelming to expose those enterprise consumers to that. You want to expose these detailed final components to the enterprise consumers in that bottom-up structure. Make sense?
Yeah, and I see that as a big area to where it's probably breaking for many customers, is they're not controlling the access or looking at the user level of the people who are accessing the top down and the more advanced functionalities.
Right, and a big key is this, proactively coaching, mentoring the users. You can bring most users up to a certain level that they can do what you want them to do. And it's key that you write this down, you publish the best practices that you want for your system so that they can go refer to it. This is absolutely key.
Yeah, I agree.
So identify the input, that top-down primary geometry. What's the output? Is it going to be components? Is it going to be space claims? Is it going to be something else? And then develop a top-down design strategy. Considering all of the things I just talked about, this is the most crucial step. The most powerful top-down design tool is a whiteboard. Do all of this before touching NX. If you have this in mind and open up NX first, it's a risky thing to do. Plan this out first. Use a whiteboard. Consult with design SMEs. Consult with the team. Especially if this is a shared top-down design structure. Some top-down design structures, only one or two people are going to use. If many people are going to use it, you've got to get everybody on board. They need to know the plan. All right. Reflect top-down design intent driver-driven relationships in the top-down assembly hierarchy. So again, the component assembly relationships essentially reflect the design breakdown of how things are going to influence other things and how those design rules will be managed. So the driver part is the wave source. The driven part is the wave destination. Driver-driven relationship knowledge typically resides with the design SME. Typically, there is at least one flexible driven component that accommodates all other driving components. Push interfaces down to the lowest common denominator of the assembly. In other words, don't do everything up here. Try and get everything down below. Less is more at the top, and more is more at the bottom. So here's an example of a electric plane that has a bulkhead, a motor, and a motor mount. Which is the driver part? Which is the driven part? It depends. If the location of the bulkhead is fixed, you've got a known thing here that you're or a thing you're designing for maximum strength and least weight. So this is the thing that you're kind of actively designing. You're buying this motor. Then this motor is being driven. Its position is going to float back and forth. But if you've got an aerodynamic shape, that's the driver. You've got this bulkhead. The motor has to fit where it's got to fit. And then in that case, the motor mount is being driven. It's got to be the flexible member that accommodates those things. So there's no wrong and right rule. You just have to establish which is the driver, which is the driven, and then stick with it. Right? Does that make sense?
Yeah, for sure.
Okay. This is absolutely key. Make the wave flow overtly clear and only one way with a top-down design assembly hierarchy of all interpart relationships. You want to maximize these. It should look like a nice waterfall flow of wavelengths through the hierarchy. Best practice, don't skip levels. Don't go from here to here. Don't link across assembly nodes. So don't go from this to over here. There are ways to do this that are a little more advanced because sometimes you need to do that. But if you stick with this as your first goal, then this will accommodate you well.
This is one of the areas where I feel like we're seeing some of our customers break down that structure, and we're seeing things backlinked, and it's more like a circular reference as opposed to one directional.
Yeah, and there are tools in NX to monitor these wavelengths, and that's always getting better.
How do you do that? Is that through Checkmate, or how would you be able to monitor?
No, I forget what it's called right now. It's Interpart Relations Browser.
Yeah, something like that.
Yep. That's what we used.
Okay. Yeah. So
we've seen some that look like the nervous system.
Yeah, exactly. And then avoid creating wavelengths in the bottom-up design or engineering structure. So avoid making wavelengths here. The bottoms-up BOMs are only intended to collect and position product components. They're not intended to provide a design hierarchy or a driver-driven relationship. They are typically have a function or installation hierarchy, so they're not structured for this one-way flow. All right. And what happens if you start making wavelengths from parts that don't have this design hierarchy but have a functional or assembly hierarchy? You start making wavelengths like that.
Yeah.
And a circular loop is almost certain.
Yeah,
right?
We're also seeing that in the detailed bottom-up structure. We're seeing wavelengths like that.
Right. And also, an unintended update is probable. You want to avoid this. Ad hoc wavelengths are not your friend. Structured wavelengths are your friend. All right. Similarly, avoid sideways wavelengths between components. Minimize these to only when absolutely necessary. Sometimes you need to make them, but try to avoid them. Component to component sideways wavelengths will also exist in the bottoms-up structure, creating a risk of unintended updates by consuming users. If they open up that bottoms-up structure, remember the enterprise consumers are working in that bottoms-up structure. But if you make these sideways wavelengths, which I'm going to show you in a second, those are happen over there as well. So if practical, push shared geometry up to the top to the top-down next higher node. So, for example, if you needed to make a wavelength from here to here, see if you can just do that activity up here and then convey the geometry in a very structured way this way. Because what happens is, if you have a wavelength and it happens from here to here, it also happens here to here. That wavelength still exists. And if these two parts see each other, there's a risk they will update. And the more of these you have, the higher the risk. So sometimes you can't avoid a sideways wavelength, but try to. Right?
What's the risk or potential? Do you think that you've outlined that? I mean, how many potential areas would they be able to fall down if they start doing this side-to-side wavelengthing?
Well, there are precautions that I provide down below in this deck that even if you make a sideways wavelength, it should minimize the chances of this. But the best approach is to don't do it at all. Right?
I just want to scare our customers as much as possible. You know.
Again, wave is great. It's very powerful, but I can use a chainsaw, but I wouldn't give it to my 5-year-old kid who's gonna run around the house. Right? A power washer is very powerful and useful tool. I'm not going to give it to a 5-year-old kid. He doesn't know what to do with it. So if used in the intended way, it's fantastic. If abused, even in a benign way, it can lead to problems. Again, from a coaching point of view, coach the consuming component designers on robust top-down design modeling best practices. Coach them to robustly model based on unparameterized waved input geometry. In other words, the things that they will be getting as top-down input in their component file, they don't actually own. How are they going to model based on that? You need to teach them how to do that. And I find in general, I'm not going to go over these in detail, but if they follow this kind of modeling process flow, they'll be fine. So here the interpart component is the input, the output is these detailed components. How these components are modeled, given that we understand that changes may happen in a topology way, or I should say in a parameterized way. So, these parts will remain, the sketch will remain, it's just going to change size. How do you model that robustly over here so that it will robustly update to these changes that are anticipated to happen? Monitor, police the structure. Given a diverse user base, benign user mistakes will happen. A top-down design structure, architects should monitor frequently. And here, it's relations browser. Here's an example. And this tool will tell you if you have links going on a circular basis, or they're going up, or this is a tool that can be used, and these tools are getting better with every release. Because remember, a wavelink has a lifespan. A wavelink is created way back here, but it goes through a lifespan. That wavelink kind of lives on forever, and how you manage that is really important. Probably the most important thing is, again, to proactively coach. Okay. In the long term, you can use Wave to develop a multi-program top-down design life cycle. Here is an example of program A, where we've gone through the primary geometry, the structure, the bottoms-up structure, and it's gone through design releases, and it's a plane. At some point in time, you're going to start changing those driver-driven relationships, those design rules, those equations, from equations to hard, fast rules. An example being here, where the radius of a fillet in the pocket of some hog out is being driven by an equation, and it goes off forever. But when you want to make that part, you want to hard code that to some standard size. And in this case, going from this 0.12463 to 0.125, you've hard coded that. You've essentially broken that driver-driven relationship. It's no longer going to morph. It's fixed. So before you start doing that, clone off a copy, make a template of it, nurture that, improve it. Then you can use it to clone off to a program B, where you have a new primary geometry, and all this downstream stuff will pretty much robustly survive. Some things might fail, but it's pretty robust. All that makes sense?
Yep.
Summarizing, use a top-down design structure to robustly enable Wave. Use a bottoms-up structure, design or engineering BOM to assemble the rest of the components, and marrying these two using an overarching product assembly as kind of a one-stop shopping thing. It really has a multiplicative effect on engineering productivity and risk reduction. Okay, so that's kind of the methods part of it. From a technology point of view, keep it simple. Keep your wavelength simple. Focus on single interpart relationships. Avoid wavelength interactions with other possibly conflicting, confusing, complex interpart relationships. For example, interpart expressions, assembly constraints. These are all interpart relationships, and having just one of them is probably the best practice. If you have wavelengths and interpart expressions, how are these things going to interact together? It starts to get complex. Lighten wavelengths as much as you can. Minimum geometry needed to convey the interface. So in this example, I think we have a front end of a jet engine combustor. These are the fuel inlet holes here, and that's needed by something else. So their position and size can be conveyed by only wave copying that face. Try to avoid wave copying the entire component. Things get heavy in that destination component fast. Updating a face is very robust. It's very fast. It's very light. Does that make sense?
Yeah, that's a good point. Yeah.
Is there any advantage to? I would assume there would be for downstream modification, but like naming the faces specifically. So then, yep. Okay.
Yeah, any attributes you can put on it will be useful to downstream consumers. They may or may not be able to take advantage of that stuff. For example, From a simulation point of view, they use named faces a lot, because they are applying meshes to named faces, and so if it's named, they can take advantage of that. You don't have to do that for all stuff, but that's nice. That's a nice enhancement.
Right.
Maximize leveraging context independent, which is the new term for this. The short term was PILO, position independent linked object wavelengths. Context independent wavelengths in product position are preferred. They can be more robust because they do not have a assembly that's managing the position. So if you don't need this feature, avoid it. Just go to this context independent wavelength. There's less kind of baggage that comes along with this wavelength. Typically, for example, if a person makes a wavelength from part a position dependent or context dependent wavelength from source to destination, the position of that wavelength is managed by the assembly part file. If you save the destination part but not the assembly part, next time you open this wavelength up, it's going to break because you didn't save in the assembly that it's managing the position of this thing, so it doesn't know about it. So there's just lots of kind of baggage, detailed baggage that comes along with these things that makes them, that tends to make them a little more or less robust to the less skilled users. So these are much more robust with respect to that because you only have this one variable. I'm going to make a wavelength. Only the destination part file knows about it. The source part file doesn't know about it. And so once you save this, it's done. It's very robust. Okay. On a similar vein, maximize leveraging product interfaces. This is a special kind of class of using wavelengths where within a part file, you publish only certain geometry that can be wavelength, and the rest of the stuff is not available to consuming users. So this is a very handy tool. It's a little more advanced tool, but it works well. Maximize wavelength configuration control. Again, you want to avoid unintended wavelengths. You want rapid wavelengths. You want structured wavelengths. You want them released. Avoid direct component to component interpart relationships and bombs. That's key. Systemically turn on delayed link update. That will minimize unintended wavelengths, even if two parts show up in the same session at the same time and the source, the destination sees its source. It won't do anything until the user intentionally updates that thing. So these are kind of layers of protection. Update following the top-down flow, the top-down structure. In other words, go from the top, update these parts, go to and release them, go to the next level, update those parts, release them, go to the next level in a very systemic way. Again, like I just said, release top-down following this updating process. Oh, one thing I missed: persistently freeze wavelengths before saving. That will internally protect that part from being updated, even if it sees its source. So that's.
And how do you do
really
that?
helpful.
What does that mean? Persistently freeze.
There's a capability in the wave control module to freeze a wavelength. It doesn't break the wavelength. It just says don't update. Even if you see your source, do nothing.
Okay.
So this delay link update kind of systemically does that.
Yeah.
The freeze link does it at the component level, and you can persistently save it that way.
Until you unfreeze it for some reason.
Yeah.
Okay.
And then breaking wavelengths is bulletproof, but it's not preferred because it's a little more difficult to undo that process.
Okay.
Alert component owners of the updated and released top-down structures. In other words, if you own the top of this top-down structure and you've updated it to a new primary geometry, you've gone through the levels and you release them, at that point in time, let the owners of the stuff below know that, okay, we're ready to go. You guys can update to these parts, right? And again, we have few users in this design structure. You have more users who are grabbing that component information and fleshing out those components and working in the bottoms-up structure. These are all design people. And then the enterprise consumers, they only see that bottoms-up structure. Most probably an engineering bomb. They shouldn't even know that top-down design structure exists. It's not relevant to them. It doesn't help them in their jobs. It will only confuse them. Consider change management of parts post top-down design. In other words, remember, the primary geometry coming into these components is not owned by that component. So how are you going to manage change on a change request basis? You know, maybe 1 year, 2 year, 10 years down the way, and that top-down structure is long faded into the distant past. Synchronous technology is a very good way to do this. Here's an example of moving some faces, traditional Boolean, and then convergent. So there are methods to use, robust methods to use to update the part, even though you might not own that primary geometry. Summary. So, given all that, I've got a demo of what an intern did for me last summer. And he did this to a rocket. He used this conceptual design kind of level single part file as his primary geometry. He has the rocket aerodynamic shape here that's wrapped around these fuel tank and rocket space claims. He has design rules of thumb that resize the fuel and engine sizes based on a change in the component payload diameter and weight. And he propagates that through this top-down structure here. And then it's mirrored in this bottoms-up structure that has all the parts, and you can see is actually more detailed. What he's going to do is he's going to do an update to the weight and the diameter of the satellite here. It's going to update this very quickly. He's going to then, because he has this top-down structure in a very overtly clear hierarchical design intent way, he can use that to his advantage and update the structure in a very robust way. But you're going to see those updates manifest themselves in this bottoms-up structure. So I'll go ahead and play that, and I'll probably stop here and there to show how this is working. So he's turned on delay update. He's changing the mass, he's changing the diameter, and the rocket just changed size that fast. Now, this whole entire update took about 5 minutes. He squished it down to about 2. So I'm going to continue playing. He's now going to go through and in a very organized way, working down through that top-down structure, update the detailed parts to that primary geometry change. So he's going to do that. He's showing the top-down structure over here, but in the main display, he's got the bottoms-up structure. So he's going through updating this lower structure and the fins. He's now updated the fuel tanks and the rocket, and now he's updated the outer shell of the first stage. And then he's just going to cascade that process to the next stage of the rocket here with another rocket fuel cells here. And that's happening right now. They're going to find their way back. So this stage is essentially done, and now he's going to go to the nose cone. And this is the hierarchical design intent flow that he put into the system. So that shows how all that was done. I want to remind you, an intern did this. I coached him, but he had basic NX skills, and over the course of one summer, he was able to do this. So it's very doable. It just requires forethought, a plan, and following the best practices, and amazing things can happen. Just saw that. So in summary, understand the general best practices and if how they apply to your specific product use case. Think if how they apply to your design process use case. Develop an executable plan. Coach the team. Then and only then open NX.
Very good.
Questions?
Thank you.
What would you say the time frame is for anybody to, I'm sure it depends on many factors, but to sort of develop this whole strategic approach for their company and implement it and roll it out?
The time frame would be weeks to months, and it's primarily key design SMEs and CAD PLM SMEs coming together and understanding all those things I talked about. What is the primary geometry? How does it influence the components below? How should we feed it through that system? What are the design rules of thumb? Once you've thought about that over a few days or a week, then it gets pretty clear pretty fast what it's going to look like. And then it's a matter of executing it. This, of course, is greatly influenced by how complex the product is.
Right.
So again, scoping, an airplane is a very complex product with thousands, if not millions, of components. But if you say, I'm not going to do this to 99%, if you're Boeing, I'm not going to do this to rivets or to avionics systems or to landing gear. I'm only going to do it to my primary structure. Now you've gone from millions of parts to 400, 300 parts.
Yep.
And again, when you show those 300 parts to a layman, them not knowing any better, they go, oh, that's a plane. That's what you're going for. Less is more.
We did this approach at Callaway when I was working there, and it's like you were saying, that's an important thing. You can't turn a driver into a set of irons, but you could turn a driver into a fairway wood potentially. Definitely a fairway wood into a hybrid.
Exactly.
But, yeah, and it really speeds things up.
Yeah, and that's, what's the topology? Is it stable? If I stay within, what are the classes of topology? Golf club is a golf club, but to your point, you found that there were classes of golf clubs where this topology was set for drivers, but different for irons. But you can make a 9-iron into a 1-iron.
Yep,
right?
Just through the part family.
That's just some modification of parameters. Geometry is all the same.
Yep. Well, thank you for presenting. This has been awesome. I appreciate it. Thanks for setting this up too, Taylor.
Yeah.
Absolutely. Yeah, it's a great presentation. I think we need to figure out how we want to distill this down and present it back to our customers. Or I was chatting with Michael, we were talking about maybe conducting a webinar, but I would say, we need to make sure that this is included in our training as well. And then figure out a way to make sure that our clients are all using these best practices.
Yeah.
Yeah, because I remember, what was it, Commonwealth Fusion? They were using Wave as a cheap and easy and way to just copy static geometry from one part to another. There was thousands of wavelengths in the bottom of the structure, and it got to the point where they couldn't open the structure, which is a likely outcome. I mean, I could have told them if they just told me that story in 3 sentences, I go, oh, well, you're eventually not going to be able to open the structure.
And I've had
It's
that
almost it's almost a certainty.
I've had that conversation with a couple people, and they're just like, "But it's so fast and easy, we love it." And it's like, we're in go fast mode right now. I'm like, yeah, but it's going to catch up to you.
Yeah.
So,
Yeah, we see that a lot, unfortunately, and all of our customers are in go fast mode.
yeah,
Seems like.
Yeah.
But that's
Yeah. Well, what was it in F1 driving? They say sometimes you need to go slow to go fast.
Couldn't agree
Is it
more.
all right if I stop the recording now since we're just chatting?
Yeah.